Time for another DrivePhysics.com video presentation. So back to the Veritasium subject of what the nature of current in a wire is. Whether the electrons have to be pushed through the wire to whatever, to have whatever happen at the other end of the wire. And his attempt to change the theory from it being conductive to it being inductive, and him saying that the whole thing is dependent on these fields. So I suppose we have to go back and draw before we talk about it, because it just makes sense to do that, I suppose. Explain. And that he hasn't changed anything, he's just changing the way he's wording it, but he's still selling the same propaganda. So the whole middle of the video is a bunch of crap about stuff that I'm saying no way happens. It isn't the story. And so then the people who were arguing against what Veritasium are saying are sort of just falling for this new way of saying the same crap over again. Alright, so you have a battery and a current and a light bulb. Alright, blah 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 blah. And the idea is you switch the battery on, the light bulb lights up, and what's the argument? That something has to happen in the wire, go through the light bulb, and go back to the other side of the power source, whatever it is. Now, the way you can cheat is with a radio, right? With like radio transmission, you just put a piece of wire, and then you have another piece of wire really far away, and you can pick up the signal. Okay, so obviously, and the closer you bring your radio to the source, okay, the louder and easier it gets to receive the signal, the light to light up, so to speak. Now, obviously, you can't light a light bulb from the energy that your radio is detecting, and what it's detecting is a frequency. So it's isolating from all the energy, all the electricity. You have a plus and a minus voltage in the antenna. The radio receiver basically takes that entire voltage and it says, I'm going to filter it for certain on and off signals. And so it's detecting a very subtle change. But actual little pieces have to hit the antenna, go at the speed of light, and hit the antenna. That's what's happening. Alright, clearly in this circuit, the same thing is happening in a way. You're setting up an antenna, and you're initializing it full of energy, full of crap. It's going to start moving. Stuff's going to start moving this way, and stuff's going to start moving this way. Whatever way, plus, minus, doesn't matter. And, that's semantics. You're going to move electrons. You're going to push them. Electron pressure is going to increase. Voltage is the pressure. Amperage is the volume. And the fact is, it's going to radiate. Okay, some of that signal is going to be radiated. Now, what's the nature of the radiation? Is the radiation part of the energy of the electrons moving, or is the radiation something else? I'm clearly arguing the radiation is made out of something else. But the fact is, some of it will radiate. You get a tiny voltage here. Now, that was always true. Okay, you could make an air transformer, okay, by just putting a piece of wire and another piece of wire, and if you shove enough voltage, amperage, through this wire, you'll create enough magnetic field effect, okay, that the other wire is going to pick it up. It's going to be energized by that field. But it's a tiny amount, okay? It's not a lot. It's a tiny percentage of what you started with. So he does the same thing here. He's got copper, instead of, he described this as being, halfway to the moon or whatever. This wire is really long. He sets up this fake experiment, that's, 40 feet long, with copper wire, copper tubing. Okay, so obviously he's going to shove a ton of amperage into this wire. Okay, a ton of amperage, and he's going to pick up an initial signal from this ton of copper here, okay, a tiny amount of voltage, and there's a light, an LED light. And so he'll say now that all the energy from this is being caused by these fields. Okay, the fields are causing the light bulb to light, which is just crap. It's not happening that way. All right, so as I've attempted to explain, what's really happening is there's no such thing as a free electron. So if you got to sort of understand that first, maybe I'll erase this. And then we'll go into the mechanics. Yeah, that would probably be the better idea. Alright, should be back. So I'm arguing that the wire is doing basically this kind of thing. There's no free electrons. There's atoms, okay? And all of the nucleuses of the atoms are positive and net. And electrons are, there's no such thing as like a free electron, an electron that just doesn't care. It just sits in the field saying, I don't care where I am, I'm not going anywhere. There's always an imbalance. There's always a positively charged nucleus of an atom somewhere that it's going to see. And obviously the only time it becomes a problem is if there's another electron right in the way. And then as it gets closer and closer, this negative gets louder and louder, so it starts seeing the negative, but it's always going to want to tend to go towards matter. So matter always has a net positive, okay, because the nucleuses are much bigger than the electron, and so the influence of the positive from a distance always is visible. And the negative part you only see when you get close enough to the atom to be right, you have an electron in the way. So it's like this pen can completely obscure my image when I put it close enough. So if you get close enough to the electron, it'll block out the nucleus. But if you're far away, yeah, nucleus is big. It's that simple a principle. So there's no such thing as a free electron. Electrons are always bound to matter. They're bound to positively charged nucleuses of atoms. You could say that. They're always going to tend to go wherever the most of them are. And so if they were in a galaxy or in a universe and you had galaxies and globular clusters, they're going to tend to go towards the cluster because it has more nucleuses in it. All right, anyway. So there's electrons that are loosely bound. That is, the atom structure has the electrons kind of close, and there's electrons that want to hang around. Okay? They don't like the electrons being there, but they can find niches where there's more positive than there is negative, and they're sort of just sitting there saying, I'm in a tension. So you can have two electrons in, say, these positions, and you can have a positive charge here, and you can have an electron that'll sit right here. Okay, it'll just say, okay, here's the atom, the material atom, and this electron is just going to find a place where this force attracting it equals the forces here repelling it. And so it ends up with a balanced position somewhere. So it's not really a free electron. It's an electron that's easily moved. That's a fact. Okay, but it's not free. All right, so the metal is full of these electrons. Okay, they can be moved around the atoms, pushed in and out of these weak bonds. And so that's what essentially what the battery is going to do, is start pushing on the electrons. It's going to apply a pressure here to this. It's going to add an electron, move an electron closer to this electron. When it does that, that has this high pressure space here. Well, that high pressure is going to divide into this pressure here, and so it's going to move this electron to here until this pressure and this pressure are equal. And that's going to change the pressure on this electron, obviously, and it's going to move its position because now it's going to find a new position that's balanced. So you're really just puffing the atoms. You're pumping in extra pressure that's going to force the electrons to get further away from each other, a little bit further away from each other, because the more electrons you add to a system, the more they have to repel each other, so the greater distance they have to create between each other to create a balance. So in a sense, atoms are getting bigger as you're puffing electrons into a system. So you could just say that the wire gets a little bigger, okay, as you pump energy in. So we'll just make this a minus just so it's electrons being added. You're adding electrons, all right, from this side. And the battery is subtracting them from the other side, but it can't even figure out it's subtracting them yet. It just knows there's pressure here. It doesn't know, you know, if you had a really long circuit, it wouldn't know that there's a plus here that's pulling them back in. So anyway, so all of that is happening inside the wire, and the key thing to understand is where do the fields come from? Where does this magnetic woo come from? This thing that travels through the space is that energy from this current? Well, obviously it's not, because you can put 500 watts in here and you get 500 watts of work out, and you can get some extra over here, okay, that you didn't pay for. So the field isn't being created by this. This motion isn't doing the work that's creating the field. The field is being created by just the consequence of you pumping in these electrons and forcing them to take up more space, that is, expand. So the expansion of the wire, essentially, okay, it's really just expansion of the atoms, but let's just say the wire is physically expanding, just as an easy metaphor. And what you're doing is changing how the universe reflects off of it. So if you understand the universe is full of signal, full of all kinds of energy flying into us all the time, and if I push out a little bit, if I push towards you, okay, you can get it that I'm pushing more energy towards you. If I expand where the barrier is, the reflecting point, you can understand that it automatically adds whatever amount of expansion I did, it adds that much extra reflection out into the world. So if you're a wire out here, okay, that reflection, that added reflection, that little boost, you're getting a perfect, say, 5 volts worth of little bits are hitting you. A certain number of little bits are hitting your wire off this other wire. I pop my surface out. Now all of a sudden you have this extra amount of reflections that are happening sooner than they would have. And that little bit of extra, okay, hits you as a signal. It's a radio signal, essentially, except it doesn't have a frequency. It just has an on, okay, off, on, okay, off, on, all right? So it's really a slow signal, but it's still a signal. It's still a change in the density of the energy. So if the energy had this density, all of a sudden you've changed the density, you've added one more bit, you've changed the density of the energy in the field, okay, that's going to hit this wire. So that change is going to hit this wire, and everything in this wire is going to have to rebalance, just like here. It's going to basically cause electricity in this wire, because this wire is going to have to expand. And it's going to expand in both directions, actually. It's going to be pushed, and it's going to cause positive this way and positive that way, both ways, until the real current shows up. So the current's going to be an artificial one, in the sense it's going to be it's not going to have a true ground. It's going to have an artificial ground created from whatever point is getting hit the most by this change in the pressure. So if the wire was going traverse, you could see it was only hitting one little point, and only at that one little point would you have a voltage difference here. Okay, but it'll create the voltage difference. And so this distance is really short between the two wires. Now he's supposed to be doing a meter, and you can see he has the two wires like a foot apart. So he's doing a lot of changes of the rules of his own experiment based on how short a distance he's using, and all kinds of replacements. Okay, this is a recipe where he's doing so many replacements that there's no way the end product's going to be the same thing, because he's replaced everything with some other circumstance. But anyway, it doesn't ever get to the real point, which is of course there's induction all the time. Any electricity traveling through a wire is creating a potential field somewhere, okay, heading somewhere, and it can be received. And the fact is I had this argument sort of with Franklin Who, about transformer, versus, radio signal. And all you're really doing is transferring electricity, because if you put the wires close enough to each other, you're inducing a real current that you can measure versus just a frequency current that you can detect and amplify. So this has no frequency, but it's going to induce a current, and it's enough current, yes, to light an LED light bulb, but that only because you put watts in over here, real watts into this wire to move a bunch of atoms. Okay, it has to be real watts, but you have to have the amps, because the amps are what's going to expand the wire. If you just have voltage, high voltage, well then you only affect, say, 10 atoms We're just making up a number. Okay, if I have just voltage, high voltage, I can just affect 10 atoms, make them bigger. A lot bigger, but bigger. And so I'm only sending a few places in the field. Okay, it's like sending much fewer particles. All right, but there's a big stream of it. So it's like I'm sending little laser beams shooting. Okay, so, but the odds of the laser beam hitting my wire now are much smaller because they're going in all directions. So I only get hit by one little laser beam. But if I increase the amperage of the wire, then I'm making more of these rays, okay? And more rays are likely to hit me if I made more rays. You can sort of understand it. The more rays of light I make, the more light I can collect. Having higher intensity rays doesn't do me much good because I can miss all of them. If you only send out, you only shoot 10 bullets with your scatter gun, but they're really big bullets, I can miss you altogether. But if I send hundreds, the odds of me hitting you are almost guaranteed. Okay, and I won't hit you with as big a bullet, but I'm guaranteed to hit you. And that's why amperage is important to creating a field. Is because you need to make a lot of atoms do what you want to have happen. You need lots of atoms to do the expanding to create a loud signal. But anyway, watts are going in and you're getting millions of a watt out. I mean, it's a tiny percentage of the electricity that takes this shortcut. And again, the electricity isn't taking the shortcut. It's the reflections off the surface that are taking the shortcut. Again, if I could just expand myself to being twice the volume, and I could make it happen at the speed of light, maybe you could understand that I'm going to get intensely bright for a second. For a millisecond, I'm going to get intensely bright because I'm going to collect all the photons within the distance of that expansion. All of those photons are going to reflect to you at one time. So I'm going to get really bright for an instant. For an instant, I get very bright. And that's all that's happening with the wire. All right, so it has nothing to do with any kind of magical electric field or magical magnetic field. The fields are not magical. They're coming from the environment. You're reflecting the environment by behaving in it. And by behaving a certain way, the other wire is getting the reflection of that behavior, and it's essentially causing it to do the same thing. It's causing it to change in the same manner that you changed. Or, in a sense, inverse. Obviously, if you're pushing, that's a pull inside the other object. I mean, obviously, you're sending something this way. That's causing a dent in the thing. It's not causing it to go out. It's causing it to go in to create high pressure. Okay, and now it has to push back out to get rid of the pressure. So it's going to do the inverse thing to you. But the point is that it's action, reaction. And the thing providing the mechanism for the reaction is the fact that we live in a universe of photons. That's why. Okay, the universe is full of energy hitting us, bouncing off of us. Anything we do changes what happens to you. That's the field. That's where it's coming from. And all this is just such bullshit. So just understand, there's nothing new here at all. He has no new physics here. This experiment doesn't reveal anything. Induction has been around since Rutherford or whatever, Faraday. This is not a new phenomenon. He's just redescribing it and throwing his own theoretical bullshit on top of it. And it's, he did this with Einstein's time dilation and had that creating the drift velocity inside of a wire. Drift velocity is bullshit. There's no such thing as the drift velocity. They're just making an average over the size of the entire wire and saying how much does the electron move over the expanse of all of the atoms in the, so you have a current going through that's only using, say, 1 out of a million atoms are being affected by an electric current, let's say. 1 in a million. And they're calculating its velocity by comparing it to all the atoms that aren't moving. So the drift velocity is a giant lie. It has nothing to do with your motion. It's like just saying only the water, like say if you're a boat and you're traveling over the surface of the water, and I want to find out your velocity. And then what I do is I say how many atoms through the whole depth of the ocean are moving this way because of your boat. yeah, obviously you'd end up going really, 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 really slow, because the only water you're pushing is this little tiny bit on the surface. So obviously it's a tiny percentage of the volume of atoms in the ocean. And so, yes, your drift velocity is going to come out to be insanely slow. So it's just such a fake. I mean, it's so, you know, ugh, this stupid woo physics. Ugh. And it gets away with it. I mean, it's just so depressing. So Electric Boom left a comment like, oh, yes, I think we're on the same page. Yeah, I think well, we should have a conversation about the parts where we're not on the same page, but we're on the same page. Yeah, I think we're saying this. Yeah, I think it's the same. It's not the same thing. Electric Boom knows. No, it's the real voltage hasn't gotten there yet. And all you're doing is getting a little tiny inductive voltage. It's a little tiny voltage you're creating. Okay, because you're pushing on the wire where it can see the signal. Oh, this is terrible. Oh, so I have to do this switching thing. And then the other guy too, the Phoenix, whatever, something Phoenix, Alpha Phoenix or whatever. He did the same thing, basically saying, oh yeah, I guess we're saying the same thing, or just saying it different, you know, same thing. Yeah. No. No. I mean, I can't, I don't even think I can play this video just because the whole middle of the video is such a pile of crap. It's just these fake animations. The whole thing is just a bunch of theoretical crap. And it's, you know, irrational theory in that, well, the magical field does this, and then the magical field does that, and the magical field is doing everything, and there's a magical field created by the magical fields, creating the magical field. They don't have a source of the field. Again, and it's so simple that the source is clearly just reflections off the wire. The wire is in the field. We are in the field. Everything is in the field. It's already there. The universe is constantly producing the field. Your cell phone is the field. It's radiating this crap. And how does it radiate it? By vibrating something like this into a field of energy. So it's going to reflect. The little tiny antenna on your cell phone is reflecting energy to the universe at different pulses, and we can detect those pulses.
About a gigantic circuit with light-second long wires that connect up to a light bulb which is just 1 meter away from the battery and switch. And I asked you, after I close the switch, how long will it take for us to get light from that light bulb?
Right, and this is a stupid question because you're not going to get light in the light bulb. Not from a 12-volt battery. You have zero chance because you're not going to get nearly enough electricity to light the light bulb. So it was all just a big fat canard. All right, and this isn't even the right kind of light bulb, blah, 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 blah. But it's just induction. All you're doing is saying, here, I want to put electricity into a wire. What's going to happen? Well, the wire is going to energize. When the wire energizes, because it's got a bunch of electrons now moving in it, okay, it's going to now reflect. One side of the wire is getting thin, one side of the wire is getting fat, you could argue. And you're going to be able to see those differences are going to fly right across this 1 meter, and the other wire is going to see those differences. It's going to be affected by them, but it's a tiny percentage of the current necessary to light the light bulb. The inductive part is tiny.
My answer was 1/c seconds.
And his answer is wrong.
We would be able to communicate faster than the speed of light.
That violates causality and common sense.
This is actually a bit misleading.
Yeah, the whole thing is a pile of crap. I mean, it's still, why can't this is almost like the Professor Lewin probing the experiment thing with the inductor. I mean, it's obvious that the inductor is going to affect your probe wires. It's undeniable that as soon as I create a coil of wire that's turning on and off a magnetic field, it's going to affect the probe wires. Can't have any other effect. It has to do that.
Misleading in a way.
Extremely unconvinced.
Naughty Mr. Veritasium has sort of a right hornet's nest.
Yeah, well, it should be a hornet's nest over that stupid image of a stupid electromagnetic bullshit field thingy, whatever, blah, 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 crap. because all of that is crap also. Okay, there's only the magnetic field, and all you're really doing is pulsing it, okay, to create something called light. And in the other case, you're polarizing it to create magnetism. But it's all just one field.
Clearly, I did not do a good job of explaining what was really going on in the last video, so I want to clear up any confusion.
There's no clearing up in this video. I don't even know if he uses the word induction anywhere in the video. I mean, he's still not getting it. He's just describing induction
that I created. So behind me, we have a scaled down model of this circuit.
So he said, the icon on his video originally said, "I built it." So he didn't do any of this shit. Some dopey university, because this guy gets millions of views, decided, well, let's do a PR thing and, we'll play along with Veritasium. So look at the wasted money here. They waste all this money to build this little fake telegraph looking thing. All right. I mean, it's all show. It's freaking copper tubing. All right. These aren't like wires. They're not a meter apart. I mean, the whole thing is just such a fake.
It is only 10 meters in length on either side. Obviously, that's a lot shorter than 1 light second. But for the first 30 nanoseconds, this model should be identical to the big circuit.
Yeah. So yes, to measure this little distance between these two is going to be easy compared to the distance traveled this way, so that we can tell the difference between how long it would take to go the full circuit and how long it would take here, because there's a 1 to 1,000 ratio, or 1 to 2,000 or 10,000. So because there's a high enough ratio, they can detect something happening this little tiny amount of time versus the time of the whole circuit. And again, all you've proven is something we already knew for 200 years, that there's induction, that when you put electricity into a wire, you're creating a signal in the field. You're changing the field, and other wires will feel that effect. So he's just proving induction, which has already been proven a long time ago. So this is such lame crap. And then he's going to pile onto that proof like, oh, well, that also proves my personal bullshit theory. No, it doesn't.
And Caltech has very fast scopes.
So Caltech, and then they got some guy from LIGO, which is just complete bullshit. So yeah, that's not exactly an endorsement.
So we'll be able to see what's going on in this.
So he says, again, in the video he says, I did it. I did the experiment. What the fuck? What was exactly your role but to show up in your Mercedes, and supervise? Say, oh yeah, it looks so special. Oh, I love the arches. Oh, the whole thing is great.
I got a ton of help on this from Richard Abbott, who works on LIGO, the gravitational wave detector. Over here, we are going to put a little resistor, which is going to be the stand-in for our light bulb.
Yeah, so it's not even, it's not even close to a light bulb. It's a little tiny resistor, as he pointed out. All right, because they can't inhibit the voltage because it's so low.
And we're going to measure it with a scope and see essentially what is the time delay between applying a pulse on the other side, basically flicking the switch, for us to get a voltage across our...
Right, so they have to use a really precise switch because they're going to detect something that's going to take place, a difference. So again, they're going to send a huge amount of voltage into this wire, our wattage, okay, through the switch. And then they're going to pick up this little tiny bit they're going to detect across these other two, this copper. And yeah, that's just induction.
Resistor. And the magnitude of that voltage is really...
Well, it was the other way around. He was installing the resistor, apparently.
Really important. A lot of people thought it would be negligible.
The amount of energy...
So again, in negligible, he's using words that don't mean anything. So he's using words like negligible. Well, yeah, it'll be negligible in the sense it won't even be close to enough to light your light bulb. And, unless, again, you're putting lots and, I don't know. You used a car battery. How many watts are you actually going... Well, a car battery produces pretty good wattage. But, I mean, how many exactly watts did you throw through that copper?
supplied by this is so minuscule.
A tiny effect, right?
The amount of power you get into the lamp over here, it's naff all.
He meant
Right. So, I mean, everybody agrees. So nothing's changed. And he's still arguing that somehow the field is creating all of the electricity movement in the wires. When clearly it's not the field, because clearly the only part induction creates is a tiny amount. And then finally the electrons show up that are being pushed through the wire. And when they show up, that's when it really turns on. So those are still the truth. And Veritasium still arguing for some, no, it's the fields, the fields, man, it's the fields, man. No, it ain't the fields, it's the electrons being pushed through the wire. They'll turn the light bulb on for real.
the light turns on at any current level immediately.
That is not what I meant.
Well,
it's not what I meant. It's exactly what you meant. Is that it's the whole point of his video is to say it's the field traveling around the wires that is causing the light bulb to light. No, it isn't. It's causing a tiny amount of inductive energy in the wire before the real electricity shows up.
actually, with that assumption, Derek's answer is wrong. The light never turns off no matter the state of the switch. Some electrons will jump the gap and result in an extremely small...
Yeah, so you'll end up, let's say you have 1,000,000 volts here, across this thing, and you can produce millions of amps if necessary. You have this little switch. Yeah, what's going to happen is that some of them go right through the atmosphere, so you end up with some voltage being created in this wire all the time, okay, even when the switch isn't closed. And that voltage will get to the light bulb. So if all you need is any voltage moving in this wire, well, you're going to have some voltage because the switch never really opens all the way. Okay, you never have a completely open circuit here unless you could do it in space and have a complete vacuum here or something. You can't create the open circuit. But anyway, so that's, yeah, if you want to get technical and you want to get silly, this is what you can do to this stupid argument. But again, the real point is that when you close the switch, this part of the wire gets energized first. And as it energizes, these two pieces of wire, as they change, because you are now letting the electrons through and you're sucking them out over here, all right, you're making this wire thin, you're making this wire fat. And as you're doing that, okay, this wire over here is going to see it happening, so to speak. Okay, this distance to see it happening is going to be a lot less than the distance of going the 300,000 miles halfway to the moon, okay, to wait for it to show up as a real signal. It'll see it first, but it's just seeing it. It's like seeing the sun burning. You're not feeling the sun burning, you're just seeing the sun burning. The real burn doesn't show up, right, until the sun gets here and burns you.
All continuous leakage current.
Let me be clear about what I am claiming. Okay, it is my claim
You're not going to be clear about anything.
that we will see voltage and current through the load that is many orders of magnitude greater than leakage current.
So he says leakage. No, that's not the argument. The argument wasn't about it being leakage across the gap. The argument is that it's induction. You're going to put a bunch of electricity into the wire. It's going to be like a transformer, a really shitty one. Okay, it's a really shitty transformer, but it's still a fucking transformer. And all you're going to do is sit there and send... Okay, instead of letting the electricity go through the wires and get to each other, you're just going to send the signal, the visual signal, okay, I'm sun, I'm hot. Right? The amount of energy coming from the sun in terms of photons is this minuscule amount of energy compared to the actual sun. Right? You're just getting a tiny residue off the wire.
An amount of power that would actually produce visible light if you put it through an appropriate device.
All right, so again, he's saying that, but why didn't he even do that, right? He didn't even do that. So all that Caltech crap, and they couldn't even do it that way. Well, if there's enough energy to light a light bulb, then you could put a little black box there with a little LED in there instead of the resistor, and you could have made the little LED turn on. So why didn't you do that? If it's the same, if it's enough voltage, we measured it, it's enough. Well, why wouldn't you do it? You went to the trouble to put up all those stupid wooden posts, do all this fucking riggedy-bickety stuff, and you couldn't go to the trouble to put an LED in there instead of your resistor and prove your point? But again, what point does it prove? It proves it's a really shitty transformer. I put megawatts into the copper on this side, I collect millions of a watt on the other side. Wow. Big surprise to everybody, huh? All the physicists are surprised. Wow, this is a real subject. No, it's a subject that was solved 200 years ago.
And we will see that power there.
Well, 158, I don't know, 175?
In roughly the time it takes light to cross the 1 meter gap. But to understand why this happens, we first have to clear up some misconceptions that I saw.
See, he calls us all misconceptions. Now, fuck you. You have the misconception that the frickin' goddamn, there's any such thing as this magical field that pops out of stuff for no reason. You have to explain where it comes from. You can't just say it's a geodesic. You know, it's just a field, you know, around it thing.
Saw in responses. Misconception number 1 is thinking that electrons carry the energy from the battery to the bulb.
I mean, it's just, no, they're not carrying it to the bulb. They're carrying it to the other side of the battery, all right? And they go through the bulb, which has resistance in it that's taking some of the, speed of the electrons. And that's being converted into the light. But, this is, of course, you need the electrons to carry it. That's the only reason why the electrons have to affect the wire. And again, the inductive part is not the energy of the electrons. It's the byproduct of the electrons moving. It's the wake they're creating. It really doesn't have anything to do with their motor and their progress. It's just a side effect. The induction is a side effect.
Let's say we have a simple circuit with a battery and a bulb operating
So he does a half hour of this crap.
at steady state. If you zoom in on the light bulb filament, you'd see a lattice of positively charged cores of atoms, the nucleus and lowest shells of electrons, surrounded by a sea of negative electrons.
Right, and they're, like, again, see how they made these all look like they're just nothing electrons. These are not nothing electrons. These are loosely tied electrons. They're electrons that are already there. And what you're doing is introducing a little bit of pressure from new electrons. So all these electrons don't go flying through the wire. Just a tiny number of electrons are introducing more pressure. And the electrons just care about the total distance. If you add up the distance between all these, like say these were free, these were bound electrons, and these were the actual solid positions. They were in these positions. They were attached to these atoms. The point is you're adding more pressure to that field, and it's going to cause all of them to have to share that pressure. The distances between them will all have to increase a little bit because of the fact that you're introducing another negative charge. So every time you put another negative charge into this matrix, this lattice, all of the electrons are going to feel that pressure eventually. And they're all going to change their position to make themselves a little further from each other, and a little further from each other, to compensate for the fact that they're being pushed into each other.
Which are free to move around the lattice. The actual speed of these electrons is very fast, around 1 million meters per second.
Well, the fact is they're not really being moved by... They're moving because force is hitting them. It's the speed that you introduce the electron will decide the speed at which the electrons are all going to rebalance the pressure. So, yes.
But all in random directions.
They're all connected to each other by forces moving the speed of light. So you have to understand there's forces, there's little bits moving the speed of light between all of the electrons, and they're reflecting those bits at each other. So it's ping pong paddles and ping pong balls. The balls move the speed of light. And all you're saying is how long does it take for this one to know what this one is doing? Well, it doesn't take very long because the ping pong ball's moving the speed of light. So obviously the other paddle moves pretty quickly. Okay, it knows it has to move very quickly. And the distance, the electrons are tiny in space, so it's like 500,000 miles between the electrons at the speed of light is the force moving. So there's a tiny amount of distance, the electron's moving 50 miles an hour, but most of the time it's the force is moving the speed of light. So it's only a tiny percentage that gets slowed down. So it's only a little bit below the speed of light that the pressure signal moves. Because only a tiny percentage of the total distance is the electron actually moving. The rest of the signal is happening over empty space at the speed of light. Most of the, as is stated, 90% of the solid material is empty space. 99% of the solid material is empty space. The empty space stuff is moving the speed of light. The material stuff that's only 1% of the material is it's moving much slower than the speed of light. But it's a tiny percentage of the total voyage, the total distance.
The average drift velocity of an electron is less than 0.1 millimeters per second.
And again, they calculate the drift velocity by calculating every single atom in this whole piece of wire. I cut a strip right through here. Every single atom, and then you divide by the one, that's moving. So they're basically averaging the speed of the one atom moving and combining it with the non-movement speed of all these others, and that's how they're calculating the drift velocity. It's to say, what are all the electrons in the entire material doing? And saying that average speed is the speed of the electricity, which is just nonsense, because clearly, of course, no, that's not how fast the electricity is moving through the wire, or the electrons. It's just absolute crap. Alright, so how much of this to play? Anyway, so the point is there's not a bunch of chaos, electrons banging into things and all that stuff is not happening. Electrons are just sensing each other's position at the speed of light, and they're changing their position. So whatever energy, if I push some energy in this way, there's no bouncing back energy. None of that crap is happening. It's pushing through, okay? It's just not pushing through in a perfectly straight line. Therefore, it's a little less than the speed of light. But anyway.
Now, frequently, an electron will bump into a metal ion.
So that doesn't happen, okay? The only reason things get hot and the only reason why conductors are imperfect is because of impurities in the wire. Impurities are what can screw up the pressure differential, because the electrons in the impurity atoms aren't connected to the electrons in the rest of the matrix of the metal. And so it's the impurities that can create heat, okay, by creating a circumstance where the electron energy is going in the wrong direction. It doesn't go in the direction of the pressure. So just more, again, he's just making crap up here.
And transfer some or all of its kinetic energy to the lattice.
So there's no kinetic energy, and so whatever we call its energy, it's not conveying it to any lattice or any of this other crap. Of course, the nucleuses are going to be affected when you change the position of the electrons. The neutrons and protons inside of the nucleus are also going to change their position subtly, okay? And so all that motion will add up to heat eventually. But again, you have to put in a lot of amperage into sometimes very tiny wires to create that problem.
The electron slows down, and the metal lattice starts wiggling more. It heats up. And ultimately, this is what causes the filament.
So, no, the filament burns because the filament isn't pure. All right, and that's why it burns. It's not a perfect conductor. It's full of a deliberate impurity.
To glow and emit light. So a lot of people will look at this and conclude the electron carried the energy from the battery to the bulb, where it dissipated its kinetic.
Yes, and that's exactly what happens, and there's the electron pressure. It's not one single electron travels through, okay? All it does is it pushes on an unpushable, it's a hydraulic system, okay? So if you understand that you can't compress water, you push a little tiny bit of water into this pipe, and that pressure has to move through the pipe to the other end, and it has to pop out. All right, and again, it goes right back through to the source again. So it's just like a vacuum pump. It's just pushing, okay? So it pushes a little bit of hydraulic pressure into one side. It accepts it back on the other side, and it just goes right through the tube, burns the bulb as part of the stream it's creating. It's just creating a stream of pressure. It puts the pressure through the dirty filament. The dirty filament isn't capable of carrying the pressure without degrading its atoms, and so they start to glow and get hot. That's all.
Energy.
And the pressure after it's gone through the filament is lower. Okay, you've lowered the pressure differential. And eventually at this other end, it's going to be zero pressure.
As heat. But consider, where did the electron get its kinetic energy from before the collision?
So again, the electron does not have any kinetic energy. You're only pushing an electron into a field of electrons that are already, it's magnets. A bunch of magnets on north face magnets. I put them in a field here, and they're all a certain distance from each other. I introduce another magnet. What's going to happen to all those magnets if they're in a confined space? Well, they're going to have to share their pressure. They're going to have to increase the pressure between them and accept it, or they're going to have to move. They're going to have to expand because of the extra pressure.
It didn't carry that energy from the battery. In fact, if the circuit has only been on for a short time, that electron hasn't been anywhere near the battery.
Yeah, exactly. But so it already happened in the wire, and all you did was induce, a sympathetic electricity in the other wire because you've changed what's hitting its surface. Oh, fuck.
So how was it accelerated before the collision? The answer is, it was accelerated by an electric field in...
Yeah, so whatever that is. What's the electric field? What is that? It was accelerated by an electric field, whatever that is.
The wire. The electron repeatedly collides with the lattice and loses energy, and after each collision, it is again accelerated by the electric field.
So again, this is all just their speculation. It really doesn't answer the question, and there's nothing elemental, that makes that make any sense. He doesn't have any source for his field. His field isn't made out of anything physical. It's not physics. This is just theology, because there's no physics in it. It's just the magical field thingy.
So, although it is the electron that transfers energy to the lattice...
So, again, he's saying it. Although the electrons are effectively essential to the whole thing progressing through the wire and getting to the light bulb and actually turning it on, yes, for a very brief moment, there's a little inductive current that gets up into the wire, but it's completely different than the actual current that's going to burn the light bulb and turn it really on. It's just a little fake induced current. It doesn't mean anything. It's like hearing the noise. Let's say noise traveled much faster than it does. And so even a nuclear bomb shows it, right? Because you see the nuclear bomb blow up, and then quite a while later you hear it, and then quite a while after that, pieces of shit start banging into you and ripping you to pieces. Well, the cosmic rays kind of, the X-rays and everything burn you up. So let's just make them very slow. But I'm just saying, obviously, that's all you're saying, is there's effects that happen when you put electricity into a wire. And some of the effects happen right at the beginning, when the wire starts expanding, and anything close to the wire can have an induced effect, induction. So again, he's not resolving any old question that wasn't answered. He's not answering any new questions. He's not adding any new evidence. He's just sitting there playing with the word induction instead of just saying the word, there's induction. And induction creates little tiny megavolt reactions. So what? Really shitty transformer. Again, he's just describing how do you make a really shitty transformer. Well, you just have one piece of wire and put a lot of voltage through it, an amperage, and then you have another piece of wire somewhere a foot or 2 feet or 10 feet away, and you see how much voltage you can collect in that wire. That's how you make a shitty transformer.
The energy came from the electric field. So where does that electric field come from? Well, a lot of animations make it look like the
So animations, that's all they have is simulations and animations. Nothing. They don't have a model.
Electrons push each other through the circuit via their mutual repulsion. So you might think the electric field comes from the electron behind it. There is the analogy of water flowing through a hose or marbles in a tube. This is misconception 2.
That is not a misconception. Frankly, that's exactly what's really happening. You're only moving a tiny distance of electrons. You're only moving a few electrons a tiny distance. But the fact is that that's pressure is real to all the rest of the electrons. It's real pressure. Like I said, you have to just move a tiny bit of fluid into a hydraulic system. Say if you have 1,000 pounds of pressure inside the hydraulic, all you have to do is move a tiny number of atoms into the vessel to increase the pressure. Just a tiny number.
Thinking that mobile electrons push each other through the circuit. That is not how
Well, they're not mobile, and you just showed them as mobile. So that's the other joke, right? So again, these are not mobile electrons. These are electrons that aren't really going anywhere. This one moves a little bit. This one feels the movement, it moves a little bit. The next one over here feels the movement, it moves a little bit. All right? There's no stream of electrons.
electrons flow in circuits. The truth is, if you average over a few atoms, you find the charge density everywhere inside a conductor is 0.
So again, it doesn't make any sense, right? Oh, the charge density inside any segment there's no higher pressure. Well, of course there is a higher pressure. Okay, but you can't measure it relative to the space here or the space here. You have to measure it relative to the other frickin' pipe that you took the atoms from. So you have to measure, if you're going to measure a pressure differential, you have to measure it from the well you took the water out of. You can't measure it, oh, well, let's compare this atom to this other atom in the bucket. No, you have to compare it to the pressure of the atom in the well. Now you've changed that differential. The well has less pressure, your bucket has more pressure.
Negative charge of electrons and the positive cores of atoms perfectly cancel out. So
again, just more absolute nonsense. Obviously, it's not perfectly canceled out until the wire is fully charged and then the pressure stops again. But it'll never stop if you keep turning it on and off and on and off, on and off. That's why those inductors, that's induction, is this changing. You keep changing the circumstance. You keep changing the reflection. Then you can communicate a signal. If you don't change it, then you can't communicate any signal because both pressurized and they stay pressurized.
Each repulsive force between electrons, there is an equal and opposite force from the positive ion.
So just more bullshit, equal and opposite force nonsense. There's no forces here. You have to describe what's causing the electron to move. Well, what's causing it to move is the field, and the field is made out of real physical stuff, and the little physical stuff is reflecting against the electrons, and it's going through the positive charges. So the stuff that makes electrons move is inert to the positive, and the stuff that makes the positive moves is inert to the negative. And that's all there is. 2 + 2 + 2 physics explains all of this.
On next to it. These forces cancel out, so mobile electrons cannot push each other through the wire.
So again, they're not really mobile. They're not moving through the wire like a beam of light. They're moving like a bunch of dominoes. They're just doing this. They're pushing on each other, sort of. But they're not moving. No electron starts here like Joe electron, and Joe electron travels all the way through the wire and goes through here and goes through here, and then Joe shows up at this end. No, Joe just passes it off to Jim, and Jim to Steve, and Steve to Fred, and Fred to blah, 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 blah.
So where does the electric field come from? Misconception number 3 is that it comes entirely from the battery.
Oh, so again, there's no huge field going through the battery because this is just more leakage current, right? So you're just saying the atmosphere is providing a path, okay, for the electron pressure to move through. So it's hitting the atoms in the atmosphere, allowing the pressure between those atoms to be conveyed to the other end. All right, so it's a leaking current, but yeah, it's a tiny, 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 tiny amount of leakage, and the energy going through the atmosphere is creating a tiny different reflective field, and so it's very little, insanely small.
This makes intuitive sense since the battery is the active element in the circuit. It has a positive side and a negative side, so it has an electric field. But this is not the electric field that all the electrons within the wire experience.
So again, it's just so silly. It's when the wire is connected, you're just extending where the battery is. So you're saying, if I attach a wire to this end of the battery, well then this entire wire becomes a pole of the battery, and the end of the battery is essentially turned into the entire size of that conductor is now just waiting, okay, to create more leakage. So if I do connect a bunch of wires to this, like if I just connected a plate to this side and a plate to this side, I'm going to leak a lot more current because now I have a lot more places to leak it.
Consider that the electric field of the battery is much larger close to the battery. So if its field were really what's pushing the electrons around, then if you brought the light bulb close to the battery, then the bulb would glow much brighter.
Yes, and that exactly will happen in your experiment. So the closer you bring the two wires to each other, the more induction you'll get and the lighter the LED will get. So if you took your two wires, instead of making it a foot and you made it 2 inches, you could get even more megavolts, a millionth of a volt. Yes, and you could light 2 LEDs. Yes, of course. The closer you put the coils of the transformer to each other, the more energy you'll keep within those two operating things, and less will leak out, and so you'll convey more of the energy to the other surface. I mean, if I have 2 plates that are shooting lights, photons in all directions, the closer I bring them, the more I create infinite plane, so to speak, and the more I break down the inverse square law, and the more I create more and more energy.
And it doesn't. The truth is that the electric field in the...
So again, to imply it doesn't matter the proximity of this light bulb to the source is just, to imply that that doesn't matter is just ridiculous. Of course it matters. It's the whole reason you're having this conversation is the battery is connected at one end, this end. Okay, it's not connected here, all right? So you have a very little antenna. And all you're doing is saying, as soon as I close the circuit, I'm just making a much bigger antenna.
Wire comes both from the battery and from charges on the surface of the wires of the circuit. As you go along the wire...
So he says this, okay, charges on the surface. Well, it's not really that there's charges on the surface any more than the fact that the side you pumped electrons into, obviously there's more electrons on that surface. And the side you're taking electrons out of, obviously there's less electrons on its surface. So yes, one side becomes positive and the other side becomes negative. But again, those effects have to travel through the wires. You have to first suck the electrons out of that wire and you have to push them into the other wire. So you're expanding the size of your antenna. Your antenna is getting bigger and bigger and bigger and bigger and bigger after you close the circuit. And all you're doing is saying, okay, now it's reflecting the universe's energy back to the universe. And if there's another wire there, it's going to see that this wire these have different pressures in them. They're sending a different reflection. One side's doing this. One wire's doing this. The other wire's doing this. So one wire's disappearing as a reflecting source. The other wire's appearing as a reflecting source.
From the negative end of the battery to the positive end, there is a gradient of charge built up on its surface, starting with an excess of electrons through to roughly no charge in the middle. As we'll see, the steepest charge gradient is actually across.
So again, you're only measuring this charge gradient wouldn't exist. There would just be electrons moving this way. So one side of the wire's pulling, one side of the wire's pushing. There's a point in the middle where the push now meets the pull and they're now in sync. Now all the wire has been engaged in the process. But it's irrelevant whether there's a light bulb there or not. Okay, so if I move the light bulb someplace else, then it's going to get more of the push before it gets the pull. It doesn't really matter because all you need is the push. because the pull is going to be automatically going wherever the pressure can escape, and the pressure can escape through the other wire. So of course that's where the pressure is going to go. So this is irrelevant. The stream can't be stopped. You're pushing water into the canal, and you're pulling water out of the other side, and it just doesn't matter whether you're pulling or you're pushing. The flow is the flow. You can't create more flow by pulling more water, and you can't create more flow by pushing more water, in the sense of you can't change when you finally get your end result of your circulation. But it's circulating from both ends equally.
The load to a deficiency of electrons, the exposed positive cores of atoms on the surface of the positive end of the wire.
The absence of electrons, less electrons on the surface. We know it's not no electrons. We just know there's less of them.
All
Less
these charges
pressure.
and the charges on the battery create the...
So you have high pressure water here, you have low pressure here. So you create the low pressure by pulling some of the water out of the bucket. You're pushing water into the bucket on the other side. It's not going to matter to the bucket. The bucket's going to say, well, same.
the electric field everywhere inside the wires. They also create an electric field in the space around the wire.
So this is all bullshit. There's no such thing as these lines don't mean anything. These lines are just telling you when there's the same amount of blue stuff and the same amount of red stuff hitting a point. And it's telling you if there's an uneven amount, then it's going to cause a bend. It's going to cause it to move in a direction. So this is just telling you what the pressure gradient is. When it's equal, you can see then it's a straight line. When it's not equal and there's more red than there is blue getting there, or when there's more blue than red, then the line is curved. The real radiation is straight line force. These curved lines are created by straight lines radiating out of the source. Okay, so the sources, like in Maxwell's drawing, are charges, and they're radiating like suns. Straight line force, and this is just a representation of where the straight line force is the same. This is just telling you like a gravitational potential. So you have a gravitational object, and you could write rings around it and say, well, this ring is 9.8 meters per second, this ring is 10.7, this one's 15 points whatever. Well, I guess it's the other way around. The numbers get smaller. So this is 9.8, this is 7.6, this is 5.2, this is blah, blah, blah. And it gets smaller and smaller and smaller as you go further out. And you can write those representations for what the gravitational field is doing. Now, obviously, these fields are going to be misshapen because it's not a spherical object. But if you could make the battery a spherical object, then there'd be perfectly spherical shells. But the shells aren't the field lines. They aren't the lines of force. Okay, the field lines aren't the lines of force. The lines of force are radiating from the object. They're the amount of photons. So if I get close to the sun, I get hit by a lot of photons. I get further and further away, I get fewer and fewer photons. These lines just represent where, at what distance you get the same number of photons hitting you. That's all the lines represent. The photons are the rays. They're the lines of force. So these drawings are just such a misrepresentation of reality. Ugh, it's just wrong. Anyway, we're into this an hour, so I guess we'll perhaps do a part 2. I don't think we've already got it, right? I really don't need to go any further, right? Let's just play his conclusion, right? I'm just show you, it's all simulations. You just keep simulating the same stuff to make some sort of argument that this is about fields, and it's all about fields, all this complex, all these fields, you're doing all of this crap. And it's just crap. And so, and then he starts doing this part where he's, well, let's replace the length of the wire with capacitors, okay? And which is just another huge cheat. Okay, let's increase the surface area, by millions of times, and pretend we're given real answers. Okay, so he has it here.
Current and lumped elements because they're more convenient than working with Maxwell's equations. But we shouldn't forget that the main actors are actually the fields.
So again, they aren't the main actors. They're a symptom of when you're pushing, when you with of the hydraulics. You push more stuff in, it expands the metal a little bit. The expansion of the metal creates an effect in the environment. It's just like noise or something else. It's a side effect. It is not the real mechanism causing the effect. It's just bullshit.
They are what carry the energy.
They don't carry the energy. So again, it's bullshit. It doesn't work that way.
And you don't have to take my word for it. This is Rick Hartley.
So again, don't have to take his word for it. I take this other guy that nobody knows from who the hell he is. Rick Hartley. He's somehow the man.
A veteran printed circuit board designer.
I used to think in terms of voltage and current. And I used to think that the energy in a circuit was in the voltage and current. But it's not. The energy.
Okay, so let's just understand. Yeah, this is always a problem for anybody who's done any circuit board work, and they've known it forever, okay, that some components are noisy. That means they're creating a field around them, and that field can induce effects in the other components that are too close to them. So that's always been true. It'll always remain true. This is something they knew when they did integrated circuits, and they have all their little wires, and yeah, they have to worry that there'll be induction between the two different wires. So this is a known fact. This isn't some new thing. But again, these effects are just talking about noise. It's just talking about getting noise out of your system. It's not talking about getting wattage out of your system. These inductors are really poor inductors. These transformer effects, this induction effect, is a tiny percentage of the energy. It's just a lie to imply that all the energy is being moved by induction. It's not.
Energy in a circuit is in the fields.
So again, it's not in the fields. It's in the wire. The wire's where the high pressure fluid is. Okay, the metal is being pressurized. The atoms are being pressurized, and it takes time for that pressure to go through the wire to get to an end place. And the fact that you're getting some noise off of that wire, okay, and you can collect the noise as energy. It's a tiny percentage of the energy, the pressure in the wire. The field effects are minute compared to the actual effects in the wire.
Most important thing you need to know is that when you route a trace, you better define the other side of that transmission line.
Yeah, there's no other side of the transmission line. You don't even have to define the other side. You have to just define whether you can accept noise in the other components, or whether you can't accept noise in them. Whether they need, what their how high your specifications, the tolerances of your specifications.
Because
again, I mean, this is comments. This is stuff I did. When I was 17 years old, I was introduced to circuit design, and this is a real problem when you start putting a bunch of, try to make the device reasonably small. You try to put everything on one little circuit board. And the problem is you have 4 components that are making so much noise that unless you isolate them on a different board, you got so much noise that you're destroying the very fine signal you're trying to detect.
if you don't, those fields are going to spread and they're going to leave you an unhappy individual.
Yeah, so again, that's perfectly reasonable to say induction is a real problem, okay, when you don't want it. All right, but that's all this is. This is just a conversation about induction. This is not a conversation about anything else. It's just induction. Yes, it's a real phenomenon. It's been happening for hundreds of years. This is not news. This is just such bullshit to say that electricity is pushed through the wire through induction. It's not.
I think one of the things that I'm most excited about the circuits video was the response videos I saw by so many people.
Oh yes, because now I'm just playing with all these other arrogant douches. They're like little baby arrogant douches, and so I can be like the pedophile of arrogant douchery. I can raise them to be arrogant douches like me. Oh God. This planet is so fucked. People are listening to this douche. All right, anyway. Shit. There's nothing to say here, right? So the sum up is somehow, oh yeah, we've all come together. We're all
especially
kumbaya.
people with far better credentials in electrical engineering than me.
Right. So they made points that you really didn't address. I don't think he said the word induction in this fucking video. I mean, he might have said it once. The whole video is about induction. Induction. Electric boom guy should just be saying, induction. It's about induction, you stupid cunt. But will you make that video? Oh, you're just creating a new bullshit theory based on a fucking old theory. Alright, you're just changing the name of it to magical field phenomenon force movement thingy. It's induction. I mean, next he'll be telling us, hey, you know what? I figured out that if I turn the electricity on and off, I can create a signal and it gets there much faster than the speed of light. It doesn't have to go through the wire. The antenna can be way over here and it doesn't even have to be connected, and I can get the signal miles away. It's amazing. Miles away. Yeah, he's going to reinvent radio for us next. Fuck. Endeavor to persevere, Gary. All right. For what point? They'll write it on my... He endeavored to persevere. And then they'll throw the dirt on the box. And that'll be it. Yeah, so what? He endeavored to persevere. Big fucking deal on this shit for whole planet. Brainless sack of shit retard fuckers. Ugh. Maybe I can get buried off planet. Anyway, till the next time and stuff. Yeah. Then you have to make a deal with Elon Musk to take my ashes into space. Fuck that. Maybe I'll induce them into space.